Hello everyone, welcome back to my YouTube channel. Today we are going to learn about AVL rotations and balance factors. We will cover how AVL trees stay balanced, different node topologies, all four relations, and Java code implementations. By the end of this video, AVL rotations will feel much easier to understand. So, first question you may think, what is an AVL tree? An AVL tree is a self-balancing binary search tree. It keeps the difference between the heights of the left and right subtrees very small. Because of this balancing property, searching, insertion, and deletion all remain efficient with O log n complexity. Now, why do we need these AVL trees? A normal binary search tree can become unbalanced after multiple insertions. For an example, if we insert value in sorted order like 10, 20, and 30, the tree becomes skipped. This makes searching slower because the tree behaves like a linked list. Instead of logarithm terms, operations can become O of n. AVL trees solve this by automatically balancing the tree. Balance factor. To check whether a node is balanced, AVL trees use something called balance factor. Balance factor is calculated as height of the left subtree minus height of the right subtree. These allowed values are -1, 0, and +1. If the value becomes less than -1 or greater than +1, the tree becomes unbalanced and rotations are needed. So how do we calculate this balance factor? Here, node 10 has height 1, node 20 has the height 2, and node 40 has the height 1. For node 30, left height is 2, right height is 1. So the balance factor becomes 2 minus 1, which equals to 1. Since the value is within the allowed range, the tree is balanced. Now look at this tree. The left side is much deeper than the right. For node 30, left height is 20, right is 0. So the balance factor becomes 2. This is outside the allowed range. That means the tree is unbalanced and we need a rotation. Before performing rotations, we identify the shape or topologies of the node. The three common topologies are straight leg, dog leg, and spider leg. These shapes helps us determine which rotation should be performed. Now let's talk about straight leg topology. In a straight leg topology, nodes continue in one straight direction. This can happen toward the left side or toward the right side. Straight leg structure usually causes left-left rotations or right-right rotations. Let's talk about dog leg topology. It forms a bent structure. The path changes directions instead of continuing straight. This type of structure causes left-right rotations or right-left rotations. These are also called double rotations because two rotations are performed. Now let's talk about the types of rotations. There are four main AVL rotations. They are left-left, right-right, and left-right rotation, and finally right-left rotations. These rotations restore balance after insertion or deletion. The first one is left-left rotation. This imbalance happens when a new node is inserted into the left subtree of the left child. In the before tree, A is the root node, B is the left child, and D is inserted further to the left. Because the left side becomes too heavy, node A gets a balance factor of positive 2. This means the tree is unbalanced. To fix this, we perform a single right rotation on node A. After rotation, B moves up and becomes the new root, D remains on the left, and A shifts to the right side. Now the balance factor returns to 0 and the AVL tree becomes balanced again. A simple way to remember this is too much left on the left side means rotate right. Now, let's look at the RR rotation, which means right-right rotation. This imbalance happens when a new node is inserted into the right subtree of the right child. In the before diagram, A is the root node, C is the right child, and E is inserted further to the right. Because the right side becomes heavier, node A gets a balance factor of -2. This means the AVL tree is unbalanced. To correct this imbalance, we perform a single left rotation on node A. After the rotation, C moves up and becomes the new root, A shifts to the left side, and E remains on the right side. Now all balance factors return to 0, so the tree becomes balanced again. An easy trick to remember is too much right on the right side means rotate left. Next, LR rotation or left-right rotation. This imbalance happens when insertion occurs in the right subtree of the left child. Because the path changes directions, this creates a zigzag pattern, also called a dog leg structure. In the first tree, A is the unbalanced root, B is the left child, and R is inserted on the right side of B. As a result, node A gets a balance factor of +2, making the tree unbalanced. To fix this, we need a double rotation. So, as the step 1, we perform a single left rotation on node B. This converts the zigzag structure into a straight line left-left structure. Step 2, we perform a single right rotation on node A. After both rotations, R becomes the new root, B moves to the left, and A moves to the right. Now the AVL tree is balanced again. A simple way to remember this is left then right means 2 rotations are required. Now, let's look at the right-left rotation. Or we call this as double rotation. This happens when a node becomes unbalanced to the right, but the new node is inserted into the left side of that right child. This creates a zigzag pattern. In this example, node A is unbalanced and node L is the right child. But the imbalance is caused through node C, which is on the left side of the L. To fix this problem, we perform 2 rotations. Step 1 is we need to do a single right rotation on node C. This changes the zigzag shape into a straight line. Step 2, we perform a single left rotation on node A. After these 2 rotations, the tree becomes balanced again, with L becoming the root of this section. After these 2 rotations, the tree becomes balanced again. with L becoming the new root of this section. So remember, right-left rotation equals to the right rotation first, then left rotation. This rotation helps AVL trees maintain balance and keep operations efficient. Now, let's look at a simple Java implementation of the right rotation. Here, Y is the unbalanced code. Here, Y is the unbalanced node. X is the left child. T2 temporarily stores a subtree. First, the rotation is performed by changing the pointers. Then, heights are updated. Finally, the new root node is returned. Updating height is very important because AVL trees depend on height calculations. This is the left rotation code. It works similarly to the right rotation. Here, X is the unbalanced node, Y is the right child, and T2 temporarily stores a subtree. The pointers are rearranged, heights are updated, and the new root is returned. AVL tree provides several advantages. They maintain a balanced height automatically. Because of this, searching is faster, insertion remains efficient, deletions also stay efficient. AVL trees are especially useful in applications where fast searching is very important. To conclude, AVL trees are self-balancing binary search trees. There are balance factors to detect imbalance. Different node topologies help identify the types of rotation needed. We learned 4 rotations: left to left, right right, left right, and right left. And finally, we looked at simple Java code implementations of rotations. Thank you for listening. I hope this presentation helped you understand AVL tree rotations more clearly. If you enjoyed this presentation, please like, subscribe, and share to NodeNotes for more computer science and data structures content. Thank you.